Okay, we're going to look at this function. It says to analyze this function f of x. So we're going to actually look at the function itself and get some information. Use the first derivative test to find extrema, where it's increasing and decreasing. Use the second derivative test to find concavity and inflection points, and then we're going to sketch this graph. Okay, so we're going to start off. We have f of x is equal to x to the fourth minus 2x to the third. So our first step is to just analyze this function. Okay? So we notice it's a polynomial. So since it's a polynomial, the domain is all real numbers. So it's true for all values. And we can also write that in interval notation in this way. Okay? The next thing we want to do is look at the intercepts. So we can start with the x-intercept. The x-intercept says let y equal 0. Okay? And y, of course, is f of x. So we take the function and set it equal to 0. I have x cubed in common, and I have x minus 2 is equal to 0. Setting them both equal to 0, I get x is equal to 0 and x is equal to 2. So that means that 0, 0 is an x-intercept, and 2, 0 is an x-intercept. If I want to do the y-intercept, we let x equal 0. So in this case, we want to find what is f of 0. So we have 0 to the fourth minus 2 times 0 to the third, and we get 0. So we see that 0, 0 is also a y-intercept. The second step we're going to do in going through this process is to what we call analyze the first derivative. So use the first derivative test. So taking the first derivative of this function, we get 4x cubed minus 6x squared. Okay. We're going to find our critical points by setting this equal to 0. We notice that there's a 2x squared in common, and we're left with 2x minus 3 is equal to 0. Setting this equal to 0, I get x is equal to 0, and x is equal to 3/2, and these are our critical values. The first derivative test says I'm going to put these on my number line. So we want to see what's happening on these intervals. So I find test values on these intervals. Let's say -1, 1, and 2. I plug them into the first derivative. I get a negative, negative, and a positive. So I put negative, negative, positive. Okay? And these were the zeros of the function. So we notice that the original function will be decreasing, decreasing, and increasing. I know when I change concavity, so I went from decreasing, not concavity, I'm sorry guys. When I change from increasing to decreasing, I have an extrema, so at x equals 3/2, it looks like we have a local minimum. Step 3 says we want to analyze the second derivative of this function. So looking at our function, we had 4x cubed minus 6x squared. The derivative becomes 12x squared minus 12x is equal to 0. Okay? And then I have a 12x in common, so x minus 1. So I get x equals 0 and x equals 1 are my partition numbers. We're going to do the second derivative test, 0, 1. But this time we're looking at the second derivative to see our concavity. So we got from infinity to 0, 0 to 1, 1 to infinity. This time I'm going to plug my values into my second derivative. So I might use -1, 1/2, and 2. Doing so, I get positive, negative, and positive. So it tells me my graph will be concave up, then concave down, and concave up. So since I changed concavity, we know x equals 0 is an inflection point, and x equals 1 is an inflection point. my last step is we want to graph this function using the information that we have. Okay. So doing so, let me space this out a little bit. Let me just start over. Okay, so since I actually have the original function, at all these places of interest, I want to use that information, okay? And so we notice that I have an inflection point at f of 0. I plug that into the original function, and so I know 0, 0 is going to be a point on my graph, okay? I know I have an inflection point at 1. I plug that back into the original function and I get -1. And so this is going to be, so this is an inflection point. This is an inflection point. What other information did we have? We have that we have a local minimum at 3/2. If I plug that in, I get -27 over 16, which is approximately 1.6875. Negative, excuse me. Let me make that look clear. Approximately negative. So I know I have a minimum at 3/2, comma, somewhere around here. This is my local minimum. If we go back to the original first step, I had an intercept here, x and y intercept, and then I had another x intercept here. This inflection point is an intercept and a inflection point and a y-intercept, right? So now I need to look at all the information I have. So I'm going to try to get it all on one screen. Okay. I know that up to 0, I am going to be decreasing and concave up. So when I come to my graph, let's do it another color. I want to decrease and concave up. Make sure I can do. Then I'm not going to keep scrolling because it will freeze up. The next point, up to 1, I know that it was decreasing and concave down. Okay. At 1, we saw that this is an inflection point, so it's going to change concavity, and it's going to be concave up again, but the function was still decreasing to my minimum. And then lastly, at 3/2, it began to increase, concave up, but we got to remember we got to go through this point of an intercept. And so this is the graph of my function.